Hello students, welcome to the course on Basic Electronics Engineering and the course code is EC201. This is the course for BTech second semester EC students and first semester CSE students. Myself, Dr. Shurajit Boshak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. So let us start lecture number 1 from the first module, that is basics of semiconductor. And the topic for the first class is conductor, insulator, semiconductors, crystal structure, Fermi Dirac function, Fermi level, valence band, conduction band, and band gap, intrinsic and extrinsic semiconductor, position of Fermi level in intrinsic and extrinsic semiconductor. So these are the topics for today's lecture from the first module, basics of semiconductor physics. And the lesson objective of this topic is study the basic properties of semiconductors, including the band gap, charge carrier concentration, doping, and charge carrier injection or excitation. And this topic is mapped with CO number 1. So let us start the first class from the first module, basics of semiconductors. So first is that you have to know semiconductor. What is semiconductor? What are the difference of between insulator, semiconductor, and conductor? So first picture is the conductor, then again semiconductor, and then insulator. A material having either completely full or empty energy band is an insulator. That is the third picture. The conductivity of an insulator is very small as no free electron is available in the upper empty band for flow of current in this material. Between the full and empty band, a forbidden region whose width is so large that at physically realizable temperature, electrons from the top of the highest field band, that is valence band, cannot be excited across the wide forbidden region to the bottom of the lowest empty band. The width of the forbidden region is called the band gap energy, whose value is actually 2.5 to 5 or 6 electron volt, or average in case of 5 electron volt. So this is the last picture which is depicted in this figure. Now in semiconductor, that means the band gap energy between the full and empty band is small, of the order of 1 electron volt. Therefore, electrons from states near the top of the lower full band will have an appreciable probability to be excited thermally across the small gap to states near the bottom of the upper empty band. Thus, a limited number of electrons will be available near the bottom of the upper empty band for conduction of electric current when an electric field is applied. The vacant states left behind by the thermally excited electrons will create positively charged empty states near the top of the lower full band, which is called the valence band. And the last is the conductor, and which is called again insulator. Where the energy band diagram are overlap with each other. That means a part of the upper region of valence band overlaps into a part of the lower region of the conduction band. Thus, a large number of electrons and holes will be available for conduction. So, this material exhibits high thermal conductivity. So, in that way, we can differentiate between insulator, semiconductor, and conductor. Next is the energy bands in solids. What is energy band? When a large number of atoms are brought close together to form a solid, the single energy level of an isolated atom is split into an energy band consisting of very closely spaced levels of slightly differing energy. It is known from the quantum theory, and the energy of the bound electron in an atom is quantized. Rather, the electron location is obtained from a probability density function, which is the probability of finding the electron at a particular distance from the nucleus. Therefore, the energy band is further divided by mainly two parts. One is valence band and other is conduction band. You have to know what is valence band and conduction band. The energy band occupied by outermost electrons of an atom, see here, that is valence electrons, is known as valence band, which is the highest occupied energy band. It may be completely filled or partially filled by electrons. And the next higher allowed band is called the conduction band, which also may be completely empty or partially filled by electrons. In this band, electrons are free to move, and the energy gap between the valence and conduction band is known as the band gap. So, you can, that is called basically, so you can know about the valence band and conduction band and the band gap energy. Now here, in between valence band and conduction band, a dotted line is present, which is actually called Fermi level or Fermi energy level. Now, so goes to the Fermi energy level, what is actually called the Fermi level. So in the next slide, we discuss about the Fermi energy level. So actually Fermi comes from the two famous scientists. One is called Enrico Fermi and other is called Paul A.M. Dirac. So Fermi and Dirac investigated the statistical behavior of electrons that occupy different allowed energy levels in accordance. So actually what is the behavior of electrons in a particular energy band? So that behavior first investigated by the famous two scientists Fermi and Dirac, and they told that the behavior of electrons is statistical in different energy levels and with the principle of Pauli exclusion principle. Now electrons in solids thus follow basically Fermi Dirac statistics. So and they establish a statistical function which is called Fermi Dirac statistics. And the probability of occupation of an available energy level E in thermal equilibrium at Tk is given by function f of E comma t. So it is a function of energy and time, which is 1 by 1 plus exponential E minus Ef by Kb into T, where Kb, it is basically an exponential function. Kb is a Boltzmann constant and Ef is a Fermi energy level. Now, probability of occupation of quantum states, which is denoted by FET, which is basically a ratio of Ne by Ge. Now, what is Ge and Ne? Now, Ge be the density of state function. Again, I am repeating that Ge be the density of state function. That is the number of quantum states per unit energy per unit volume, and Ne be the number of particles per unit energy per unit volume occupying the quantum states. So therefore the Fermi distribution function is actually plotted in this figure for several values of temperature. Now the physical meaning of EF at T equal to 0 Kelvin say is that Fermi energy level is the highest occupied energy level at absolute zero temperature. In general, Fermi energy level may be defined as the energy level whose occupation probability is half. At T equal to 0 K, the Fermi distribution function is a step function. Step function like say Fe equal to 1 for E less than Ef and Fe equal to 0 for E greater than Ef. The electrons occupy the lowest possible energy states so that all states below Ef are occupied and those above Ef are basically empty. Now, as the temperature increases, See in the figure. As the temperature increases, the distribution function varies rapidly from nearly unity to zero, nearly zero. That is, the step function is basically now rounded off. Rounded off means the boundaries of Fermi step are blurred over an energy range of few times kT around the value of E equal to EF. So assuming that Fermi energy is independent of temperature, now at T greater than 0K, the thermally excited electrons can jump from field levels below EF to empty level above EF. The probability of occupation, therefore, the probability of occupation above EF is now greater than 0, while that below EF is less than 1. The area of the curve under the distribution is basically a increasing in order. Now at T equal to 0K, see, at T equal to 0K, when E less than EF, therefore this term exponential E minus EF by KBT is basically e to the power, it tends to e to the power minus infinity, which equal to 0. Thus, Fe for the condition of E less than EF equal to 1. Now at T equal to 0K, when E greater than EF, e to the power E minus EF by KT, when E greater than EF, then this is it exponential to the power infinity, e to the power infinity, which tends to infinity. Therefore, Fe greater than E greater than EF equal to 0. Now at T greater than 0K, if we put equal to EF, now at T greater than 0K, if we put equal to EF, then see F equal to EF equal to 1 by 1 plus exponential 0 equal to 1 by 1 plus 1 equal to half. So at T greater than 0K, E whenever E equal to EF, see in the earlier figure, so at when E equal to EF, so Fe Fermi level is basically consist of half. So this is mathematically proved here. Okay. Now come to the point that what are the different types of semiconductors are present. Intrinsic semiconductors and extrinsic semiconductor, these are the two different semiconductors are present. Now a semiconductor, so first let us start from intrinsic semiconductor. A semiconductor in which electrons and holes are generated solely by thermal excitation across the band gap is called an intrinsic semiconductor. Thus, the electron concentration in the conduction band is equal to the hole concentration in the valence band for an intrinsic semiconductor. So here the Fermi energy level of an intrinsic semiconductor is basically exist in the midway between valence band and conduction band. So in other words, Fermi energy level of an intrinsic semiconductor lies close to the middle of the forbidden gap. Now silicon, for intrinsic semiconductor, silicon is the most important and widely used semiconductor in electronic devices. Silicon processes basically the diamond structure. Each silicon atom has 4 valence electrons shared by 4 valence electrons of neighboring atoms to form a covalent bond. Thus, the valence electrons are tightly bound to the nucleus, and these electrons are not free to move. Thermal agitation breaks the bond, and the electron gain sufficient energy. See, this is the free electron. Now, this free electron gets sufficient energy to be excited from the valence band to the conduction band, which means removal of an electron from a covalent pair bond. Now, this electron is released to be free in the conduction band to behave like a charge carrier to conduct current through silicon crystal. The excitation of electrons leaves behind an empty state, a localized defect in the covalent bond structure, which can be occupied by another electron by breaking covalent bond, by just breaking the neighboring covalent bond. This empty or vacant state is referred to as holes, which acts like a positive charge carrier and can wander around the valence band. An electron in a covalent bond pair to the hole may easily occupy the valence state, completing the bond pair but transferring the location of hole to the site from where the electron occupied the vacant site. So, in that way, intrinsic semiconductor are present. Now, next is the extrinsic semiconductor. Intrinsic semiconductor are pure semiconductor which possess some interesting properties. But real use of semiconductor lies in introducing very small amounts of impurity or dopant atoms, in which case the semiconductor would be extrinsic. That means some impure or doped whose conductivity and other electronic properties can be altered. See here, the extrinsic semiconductor is an impure semiconductor formed from an intrinsic semiconductor by adding a small quantity of impurity atoms, which is called basically dopants. And the process of adding impurities to the semiconductor crystal is known as doping. So this added impurity is very small, of the order of 1 atom per million atoms of pure semiconductor. Now, depending upon the type of impurity added, the extrinsic semiconductor are classified as P-type and N-type semiconductor. Say for example, if pentavalent impurity, pentavalent means who are in group 5 element in periodic table. So for example, if pentavalent impurity like phosphorus, arsenic be introduced in tetravalent silicon, then semiconductor would be basically N-type. On the other hand, if a trivalent impurity like boron be introduced into the tetravalent silicon, then the semiconductor would be P-type. The significance of the nomenclature of N-type and P-type semiconductors can be understood in the next slide. So first we start from N-type semiconductor. Simple two-dimensional picture of single crystal tetravalent silicon lattice is doped with a pentavalent element belonging to group 5 of periodic table, such as phosphorus is introduced in silicon crystal as substantial impurity, that is impurity atoms which occupy vacant lattice of silicon. Now, out of 5 valence electrons of group 5 impurity atom, say phosphorus, 4, see phosphorus have 5 valence electrons. Now, out of 5 valence electrons for phosphorus or group 5 element, 4 would be used to form the covalent bond or covalent pair bonding with neighboring silicon atoms. 4 are used, say in the figure. The remaining 5th electron is weakly bound to the impurity atom. This is the remaining free electron, which can easily be detached or ionized by thermal excitation at ordinary temperature, which can be free in the conduction band as extra conduction electron or extra free electron in the conduction band. The impurity atom, that is phosphorus, becomes positively charged ion now because of losing or donating its 5th electron to the conduction band and remains fixed or immobile since it is strongly bound to the neighboring 4 silicon atoms by covalent bond. In this case, more electrons than holes will be available as charge carriers, and the semiconductors are called N-type because majority of charge carriers are negatively charged electrons. So that In that way, N-type semiconductor can be formed. So what is the Fermi level for N-type semiconductor? Therefore, the Fermi level of N-type semiconductor is now close to the, see in the first figure, close to the conduction band. And the Fermi level for p-type semiconductor, I come in the next slide, where first I want to describe about p-type semiconductor. Next, I move for the Fermi level. So next is the p-type semiconductor. In case of p-type semiconductor, if a trivalent impurity, that means a group 3 element such as boron is introduced as a substantial impurity in tetravalent silicon, one covalent bond appears to be empty, because see here in the boron have 3 valence electrons. Now adding boron to pure silicon crystal results in lack of an electron and it becomes a hole. So the 3 valence electrons of boron are shared by neighboring silicon atoms to form covalent bond. The fourth bond is not formed and there is a vacancy in the bond. This vacancy in the bond is occupied by electrons in the valence band by gaining a small amount of thermal energy to form a covalent bond. Thus, boron atoms accept electron from the valence band and vacancies are created there. This vacant position in the valence band can be thought of as hole. So this is basically a hole. See in the picture. So this figure shows the formation of holes in the valence band, and these positively charged holes can move through the crystal contributing current. Boron atom becomes negatively charged after accepting the electrons whose discrete energy level just lie above the valence band of the forbidden energy gap called acceptor level. So see the Fermi energy level of p-type semiconductor. Here it is near the valence band. Because of the hole, free holes are present. Since holes are the majority carriers, these semiconductors are called p-type semiconductor, where electrons available in the conduction band are minority carriers. So boron atoms are called acceptor atoms because they accept electrons from the valence band and are negatively charged fixed atoms. Okay. So this is all about p-type and n-type semiconductor. So actually In the N type, that means number of electrons are larger in the conduction band. But in P-type semiconductor, number of holes are larger in the valence band. In case of N-type semiconductor, remember that group 5 elements, that is pentavalent elements, are added with the group 4 element, that is silicon or germanium. But in case of P-type material or P-type semiconductor, trivalent electron or group 3 elements, that is boron, such as boron, are added with the group 4 elements such as electrons. So naturally boron have 3 electrons, so one hole are generated, and that holes generally thermally excited to break the another covalent bond. So naturally number of holes are getting generated more than the number of electrons in case of P-type semiconductor. So that's all about P-type and N-type extrinsic semiconductor. So let us stop the today's lecture. From the next lecture, we start from the mass action law, drift and diffusion phenomena. So thank you so much. Now I am ending the session.